Algebra 2 students, this is Mrs. Tran-Bloom recording for our second unit. This is section 2.1. So in unit 2.1, the title of the entire unit is called Graphing and Analyzing Functions. Now I know a few of you pick up some packets or the notes and homework packet from our school, and you guys picked it up with either Mrs. Lloyd or Mrs. Lassner. We have changed a few things. So if you later see these stars or asterisks next to a word or a graph, meaning that we change a little bit. So what you have to do is modify it on your packet, okay? So section 2.1, features of functions. Analyzing a graph means looking at and describing the characteristics with numbers or number phrases. We describe these key characteristics with mathematical notation or math language. So below this right here in your notes packet, they are all blank. So what you need to do is probably hit pause and write it down. And now as I'm reading through them, I'm going to be explaining them and maybe draw out some pictures, okay? Domain and range, which is the first two. I'm pretty sure you guys have heard these from Algebra 1 already. So the domain of a function is the complete set of possible values of the independent variable. Usually we use x for our independent. Sometimes we even use the word input variable, okay, or just input for short. So independent input x, usually they mean about the same thing. In other words, the domain is the set of all possible x value. The range is very similar, except the range of a function is a complete set of possible values of the dependent, okay? In Algebra 1 and Algebra 2, we normally use y. Now, dependent, sometimes we would use output. In other words, the range is the set of all possible y values. A function is a relation between two sets that associates every element of the first set to exactly one. Okay, so this is a keyword right here. Every element of the first set to exactly one element of the second set. More commonly known as each input, which is x, has exactly one output, which is y, or sometimes we use f of x to represent the output. For each value in the domain has exactly, or each value in the domain has exactly one value in the range. Another way to look at a function is if no vertical line intersects the graph of a function, sometimes we call it f, in more than one point. So what do I mean by that? So let's give you an example. Let's make a simple one right now, which is a parabola. And it said, okay, well, each input can only have one output. So if input meaning x, so if I were to draw this first x line, can you see that there's only one y value right now, which is whatever that y value is. Let's call it y1 and x1. What if I draw another x somewhere else? Let's say this is x number 2, and as you can see, there's only one y value. Let's call it y2. So that's what it means to be a function. Now, as I'm drawing more and more lines on that's crossing the x-axis, these are all vertical lines, okay? And the definition said, well, another way to look at it is if no vertical line of the graph intersect the graph of the function, let's call it f, more than one point. So if it intersects more than one point, then it's not a function. So what is an example of a non-function? So let's move it over here and make another graph that's not a function. How about a sideways parabola? What if I draw one x, right? Let's call it x1. Look, I intersected y1 and there are two y's. So in this case, there are two y's for that one particular x. So this is not a function, okay? Now, as you can see, my vertical line, okay, so I'm going to go draw a few more vertical lines. Vertical lines is intersecting this graph more than once. So that's why it's not a function. So a function meaning that for every x, there's only one y, or it passes your vertical line test. When I say pass, it cannot intersect more than once. Now, a one-to-one function, it's even more strict. A function f is one-to-one if no two elements in the domain of f correspond to the same element in the range of f. In other words, exactly, each x in the domain has exactly one image or one value in the range, and each y in the range has exactly one image or one value in the domain. Another way to look at one-to-one is if no horizontal line intersects the graph of the function f in more than one point. Okay, so a one-to-one function is even stricter than a function. So to be a one-to-one, you have to first be a function. So currently, if I were to, again, draw out the parabola, this is a function. So we know that from the previous proof. But what's happening that it's even stricter. This time, I'm going to, it says that, hey, you know what, not only that one x maps to one y, now one y also maps to one x. So here, let's draw this first y. So this is y number 1. Oh no, right? It has x number 1 here. It intersects x number 2 here. So right now, one y is mapped to two x's. So that's not okay. Now, if I keep on drawing multiple lines like this, well, every line I've drawn so far, those 3 lines, every line, every one y value, all of them all have two x's. So this is not a one-to-one, okay? So this is not a one-to-one. So it's a function, it's just not a one-to-one function. So what's happening is, as you can see down the bottom, it says here, another way to look at one-to-one is if no horizontal line intersects the graph of the function more than one point. So usually we say, okay, it passes the horizontal line test, meaning that we can only, when we intersect it, right, when we draw a horizontal line, it can only intersect one or less, okay? Now, well, how about the Sideway parabola that we proved earlier? This is, earlier we said it's not a function, even though, as you can see now that I'm drawing the horizontal line test, so this is y1, would you agree? This y1, what's happening? It only intersected one x place, right? x1. But it's not a one-to-one because it wasn't even a function in the first place. So if it's not a function, it's not a one-to-one function. So that's not a one-to-one. Now, what would a function look like then? I'm sorry, what would a one-to-one function look like? How about this? So first, you have to prove that it's a function, meaning that one x can only intersect one y. So here's x number 1. Nice. There's only one y value that is crossing, right? So that works. So it doesn't matter how many vertical line tests I'm going to draw, it will always intersect one point. Now, how about horizontal line tests? If I draw a horizontal line test, meaning that one y, let's call it y2, one y is mapped to exactly one x. So this one is a one-to-one. Yes, a one-to-one. Okay. So again, a function, so a one-to-one function must be a function first. X-intercept is where the graph or the function intersects or crosses or touches the x-axis. The y value is always 0. So usually when we write the x-intercept, we write it like this, x comma 0, whatever that x value is. Y-intercept is where the graph or the function intersects, crosses, touches the y-axis, and the x value is always 0. So if x is 0, we always write 0, comma y, whatever that y value is. Now, maximum and minimum, we are going to use this very loosely, okay? In Algebra 2, we will consider a high point on the graph as a maximum. So think of it as a peak. So if I give you a made-up graph here, like that, okay? And so a high point meaning this is a maximum, and this is also a maximum. So think of it as the maximum and minimum, think of it the vertices, except that the max will be the high. So this is max, okay? And in there it says plural is maxima. Now, the low point, so we got this one and we got that one. Those are the minimum. Okay, so minimum and minimum. In pre-calc, you're going to learn more of those later. Inflection point is where the function or the curve goes from concave upward to concave downward or vice versa. Normally, you're going to have an inflection point in something like this. Okay, like a cubic graph. Oh, that is such an ugly cubic graph. Sorry. All right, like this. Okay, still ugly, but I'm trying my best here. So that point in the middle right there, that's a inflection point. Okay, so that's an inflection point. So what's happening, concave up and concave, this is concaving downward. Concaving downward meaning is like this, okay? And then this over here on the right side is concaving upward, meaning that it's like this. So that's what's happening. So an inflection point is where the function or the curve changes from concaving up to concaving down and vice versa. Now we're touching on the vertex. Vertex is the highest or lowest point, also known as the maximum or minimum. Okay. Now we touched on the vertex a little bit already earlier when we were talking about the maximum and minimum. Usually in a vertex, guys, where a parabola would have a vertex. Sorry, I'm trying to switch up the pens. So a vertex, let's see, we have a parabola has a vertex, right? So this is the low point. And then if we have an absolute value function, let's say this is an upside down absolute, that's also a vertex. So turning points. Turning point is a point of the graph where the graph changes from increasing to decreasing, aka rising to falling, or vice versa, decreasing to increasing. We can think of it as where the local maximum or the local minimum happens. Okay, so in here there's a fancy word called local maximum and local minimum. Don't worry about those, we'll cross that out for now and just think where the minimum and maximum happens. So let's go back to this graph up here that I already had a sketch. I'm gonna get a different color pen. So when we have increasing, so can you guys see, and this concept right here is super difficult, so make sure you guys are paying attention. It says here, okay, increasing is when the graph changes from, turning point is when the graph changes from increase to decrease. So here's a turning point, that's where the max is, and here's another turning point where the minimum is. Here's another turning where the max is, and here's another turning point where the minimum is. So that example right there has 4 turning points. Now, in a little bit, we'll talk about the increase, decrease to connect with those turning points, okay? End behavior. The end behavior of a function describes the trend of the graph, which of f of x as x approaches positive infinity or negative infinity. So now let's go back to that same example that we have already. So when x approaches positive infinity, which we in Algebra 2, we use the symbol x, and then the arrow means approaches, and then positive infinity. As you can see, when x gets really, really big, so think about it as x gets to be 1 million, okay? Which obviously, according to my graph, I can't really sketch out that far, but because of this arrow right here, class, okay? This arrow right here said, okay, as x goes to the right, y goes up, right? As x goes to the right, y goes up. So what happened is in mathematics, we write y also approaches infinity. So in verbally, we say as x get to be 1 million, y increases, right? Y goes up, or let's say y goes up. Y goes up to, who knows, 1 million, 10 million. We don't know what the exact number is because the arrow indicates just goes up. So this right here is how we say as x increases, or x goes to the right, y also increases. So that right here is the right end behavior. Right end behavior because it's on the right side. Now, how about the left end behavior where x is gonna go to the left? So this arrow right here is saying, okay, remember this keeps going down and out, right? I mean, just because we stop right there because the paper doesn't allow us to go any further. But as x goes out to the left, okay, so x approaches negative infinity. When you see negative infinity, I want you to think about a negative million, negative 10 million. What is the behavior of y? Is y going up? Is y going down? In this case, y is going downward. So y also approaches negative infinity. Now, is it always like this? No, it is not always like this. Would you agree? So what if I go like that? Okay. So for that example, as x approaches negative infinity, y is going upward. So we say, okay, x approaches negative infinity, y approaches positive infinity. Now on the right side, as x approaches, right side means a million, positive number. X approaches positive infinity. Y is going downward, so y is approaching negative infinity. So as you can see, they can mix, right? One can be positive and one can be negative, and vice versa. Or both of them can be positive or both can be negative. So that's what's happening to the end behavior. So think about the end behavior is what's happening to y when x approaches a really large number, either positive large number or either negative large number. Now, increasing interval is when y values get bigger or when they go up, when x gets smaller. We write the interval as follow: x1, x2, where x1 is smaller than x2. Okay, so I'm going to, and then decreasing is similar. So let me just sketch another graph down here. There, okay. So we have, this is the maximum, okay? And then we have minimum. This is the minimum, and this will connect to, and these also called vertices, vertex, right, with 3 vertices. Increase and decrease, super difficult. Let's call this first x right here, x1. This second x right here, x2. And this point right here, let's call it x number 3, because we don't have an exact value since I just made a sketch. Well, it says increasing interval, it's when y values get bigger and bigger, they go up. Okay, well over here, we don't know what this is, so let's call it negative infinity, and over here somewhere, positive infinity. So currently, there are 4 intervals. So this first interval is, and remember it says here, we always write the interval from small x, comma, big X. So negative infinity, comma, this next x over here is x number 1. So we're going to say x number 1. Now the second interval over here, up here on the top, that's first x, here's the second x, we call it x number 1, comma, x number 2. Then third x down here, we can say, okay, well this interval is x2, comma, x3. And we haven't really decided which ones increase and decrease. And then this over here, this goes all the way, this x goes all the way from x number 3 to infinity. These are just saying, okay, from to separate the vertices. Now, which ones increase and which ones decrease? We are now going to look at the y values, okay? As I go, so pretend that you're walking on this number line. As you're going from here, right, all the way towards our first x, is this y going down? Yeah, the y is getting less and less and less. So this first interval is decreasing because the y value is getting less and less. Now, and then keep on going. As you're going, again, from left to right, what's happening? Are you climbing here? Yeah, you're working harder, right? You're going upward. So this one right here, you are increasing. So from from x1 to x2 is the increasing interval. So I want you to think with increase and decrease, are you climbing? So climbing means you're increasing. Or are you sliding down? Okay, sliding down means you're decreasing. So that's what's happening. So from x2 to x3, you are decreasing. And yes, this is super confusing. Increase and decrease intervals are the most difficult concept to understand. Then you're on the last one, the last interval from x3, comma, infinity. Well, this one, you have to work you have to put more energy to climb up. Would you agree? Because it's going up, the y value is going up. So this one, you are increasing. So that's how we determine if it's an increasing interval or decreasing interval. And we only write the interval using x's, okay? We only write the interval using x's. Now, and we always write the smaller x in front of the bigger x. And that takes care both of the increase and decrease. Now you will see the word evaluate a lot. And to evaluate, we just have to determine or find the value that we're asking for. So now that we have all of our vocabulary defined, let's put it to practice. This first graph looks like we have a V graph. So we have to fill out all of these information right here. First, we have to find the x-intercepts. There are two x-intercepts. One is over here at 3, 0, and one of it is at -3, 0. And yes, guys, make sure you write it as a point. And it's -3, 0, and 3, 0. Remember, x-intercept is where the graph crosses or touches the x-axis. Y-intercept, we happen to have one as well. That's at the vertex, and that's 0, -3. Remember, y-intercept is when x equals to 0. So 0, -3. The domain is talking about what all of the x values that we can possibly have. And as you can see, it keeps going to the right forever and keeps going to the left forever. Oh, by the way, in Desmos, as we teachers use Desmos to graph out the functions, if you don't see any close dots in the ends here, I mean they do go on forever. Whenever you guys see the dots in the end, like that, okay, that means they do not go on forever. So if it's open or closed dots, I mean they do not go on forever. If you don't ever see the dots, then that means they do go on forever. So the domain means all real numbers. Also, we could write this as an interval notation. All real numbers meaning that it can start from a -infinity over here because this graph goes to the left indefinitely, and it ends at somewhere which we don't know because the arrows mean they go right indefinitely. So when we write the domain, we write -infinity to infinity if we choose to write it as an interval notation. And yes, we're gonna practice interval notation as well. The range is talking about all y values, okay? So what is the smallest y value that we see? It's right here. The smallest y value is at -3, and it goes upward. Oops. So back in the days, we say, okay, y is really bigger than or equal to -3. And the reason it equals is because it is on -3. Now, interval notation, because the arrows go upward, meaning that at some point, we don't know when, it's just going to hit 1 million, 10 million, 100 million. So in interval notation, we write a bracket, and I will explain the bracket in a little bit, from -3 to positive infinity, meaning that, okay, at some point, it's going to keep on going and going and going forever. You can't stop it, right? So if someone said, well, what if it stops at 10 million? No, it doesn't. Okay, it can go up to 100 million. Now the bracket, this bracket means it's inclusive. That means it can be -3 versus the parentheses. The parentheses mean it cannot include it. Okay, it's non-inclusive, meaning that it won't be. So if you have -3 to infinity, meaning that this graph does not touch, okay, the graph doesn't touch -3, which is false in this case. In this case, the graph does touch -3 on the y value. So the bracket means inclusive, and the parentheses mean non-inclusive when we're using interval notations. Now, why do we always use parentheses on the infinity? Well, because we don't know what infinity is, right? That's why we can't include infinity. Your large number could be 1 million. But I could be 1,000,001 and someone else could be 5 million. So that's why the infinity numbers will use parentheses all the time. Vertex or inflection point. For this particular case, it is definitely going to be a vertex, and the vertex is at 0, -3. Is it a maximum or minimum? This is definitely a minimum, and the minimum is where the vertex is at. Now, end behavior. This is a new concept to us. Remember, we talked about end behavior is what is the behavior of y as x is going towards negative infinity. And negative infinity is all the way over here. So as x is going towards negative infinity, y is going up. So that means y is approaching positive infinity. Similarly to, hey, where is y? What's happening to y as x is going towards positive infinity? If x is going towards positive infinity, y is going up as well. And yes, both y's could be positive and both y could be negative. Increasing and decreasing interval. So let's find the vertices and break that up. The vertice currently it's at x equals to 0. Okay. Now we don't have any other vertices, so we're going to use intervals of negative infinity and then positive infinity. So the first one we're going to write is negative infinity to 0. The second interval is 0 to infinity. Now mind you, increase and decrease, we have to use x values, and we have to write the x values from small, comma, big. So earlier we talked about increase and decrease. Decrease meaning that can you slide down on the curve? And this one you can. Whee, whee, right? So this side it's decreasing. Now on the right side, whoa, you're huffing and you're puffing because you have to hike this track. So this side is increasing. Okay, so increasing interval is from 0 to infinity. Decreasing interval is negative infinity to 0. And no, it's either increasing or decreasing or maybe later constant, but they can't be the same. A function can't increase and decrease over the same interval. Next piece, is this a function? Okay, remember we talked about a function meaning that only one x, right? One x maps one y, so or passes the vertical line test. So if I draw infinitely many vertical line tests, it's the x value, in this case, touching or more than one time. In this case, whatever x I draw is only once. So this is a function. So this is yes. Is it a one-to-one function? So a one-to-one function proves that it has to be a function first. After you prove that's a function, now every y value can only have one x. Uh-oh. Okay, that's a problem because here's y number 1. y1, I got this dude over here, that's x number 1, and this dude over here is x number 2. So this one y value has 2 x's. And as you can see, that horizontal line intersects twice, meaning it did not pass. So this is not a one-to-one. Evaluate f of 2. F of 2 meaning that when x is 2, what is y? So I'm going to find 2 on x and draw a line. Beep, 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 beep. So there's x equals to 2. Okay. Now y is right there. It intersects y right there. And right there means the y value is at x. So this right here, it's 1. So f of 2 equals 1. If I can get my pen to work.